Hello, everyone. We move on to study lecture 2 of module 1. The title is Action Planning. Before we enter the study of lecture 2, let's have a quick review about the learning objective. So this slide remind you about the learning objective of this course. The learning objective is for you to become a designer of a robot as a product. As a designer of a robot as a product, you must know the answer to these 4 basic questions. Question number 1, who are the user? Question number 2, what are the needs of user? Question number 3, what are your robot which could meet the need of your user or buyer? And question number 4, what are the solutions behind the design of your robot? In lecture 1, you understand that we may face 2 types of user. One is the category of specific user. Then in this case, you must follow the need of this specific user in order to guide the design of a specific robot as a product. The second case is the situation in which we do not know the specific user, but we could imagine some generalized user. Then in this case, we can identify the generalized need from the generalized user. Therefore, you will be able to answer the first 2 questions without knowing specific user. In this way, you will be able to design and implement and produce your robot in advance. Then try to find the buyer user, through the process of marketing and the sales. All right. So therefore, you understand the purpose of module 1 is for you to know generalize the user and generalize the need from this generalized user. And we use manufacturing industry as an example to illustrate the nature of a generalized need from generalized user. And the conclusion, the solution, the principle are applicable to other type of robot in other domain. All right, so that is the key takeaway from the study of module 1. And in lecture 1 of module 1, we have studied the process of task planning. So task planning will take a job description as an input and produce a sequence of task description as an output. Now we move 1 step deeper. So you will see module 1 actually is to transform the descriptive input into technique output in the form of equation. Because once we obtain equation of motion, then robot will feel comfortable to perform or execute the equation. All right. So the first step toward this direction is to transform job description into task description. Then the second step is to transform task description into action description. And slowly we increase the level of technique detail until we obtain equation, mathematical equation. which describe the motion or which describe the generalized need from the generalized user. All right. Then, as a designer, you should know how to draft out the blueprint of your robot. This slide gives you a general guideline for you to plan the blueprint of your robot. And from this slide, you can identify the module that we are going to study in this course. For example, module 1 is about the robot man, which will transform the description of a job task all the way to the equation of the motion. You see, all these are the equation of the motion with motion parameter in path space or joint space. You can also identify module 2, which is about the design of a robot's body, which will perform the motion. And you can identify module 3, which include the study of kinematics, the study of dynamics, okay? And module 4 is about the study of robot control, all right? So therefore, in order to master or understand this blueprint, you need to study all these topics which are categorized into 4 modules. So module 1 is about the robot man, module 2 is about the design of a robot's body, module 3 is about the modeling of robots, kinematics, dynamics, and statics. Module 4 is about the control of robots' motion. All right. So with this knowledge, you should be able, okay, to come out the detail of this generic blueprint of your robot. All right. Now we enter the study of lecture 2 of module 1. So then we start with the study of the idea about the purpose of action planning. Okay, so this is the definition of action planning. So action planning basically take a task description as an input and produce a sequence of action which could be performed by robot. Okay, so from this slide, you will see we slowly increase the level of technical detail, because in the left-hand side, the job description usually is in the form of a human language, okay? And without much technical detail. For example, my job is to produce a car in big quantity, or produce 1 million of a vehicle per year, per month, or something like that, or produce 10 million of a handphone per year, per month, etc. All right, but since today's robot have not yet reached the level of intelligence which could match with a human level of intelligence. Therefore, we as a human being must help the robot to do all this planning and slowly increase the level of technical detail all the way until we obtain the equation of a motion. All right. Then next question will be, what are the actions that the robot can perform? Okay, so the answer will be robot could perform 2 types of action. One is related to manipulation, and the second one is related to locomotion. Okay, manipulation include grasping and movement of the arm, etc. Okay, locomotion include view is the locomotion, leg is the locomotion, etc. Now I'm going to show you some example which will convince you about the answer in this slide. Okay. For example, robot could perform manipulation, which include open, close, move, pick, and place, etc. All right. And here is one more example which demonstrates to you the action which could be undertaken by robot in terms of manipulation. And this video show you another example of action taken by robot for manipulation. I just quickly run through the video. Okay, so this is a typical scenario of hand-eye coordination. For viewing the locomotion, here you will see the effort that we spend toward the achievement of making vehicle to become a high-speed mobile robot. All these are unmanned vehicles, so you can treat them as a high-speed mobile robot.
From Blacksburg, Virginia, Odin from Victor Tango's team number 32. Number 3 on the south end of the free zone from Stanford, California, diesel-powered Volkswagen Passat station wagon. Junior from Philadelphia, PA. Ben Franklin Racing Team, bot number 74, Little Van. Bot number 79 from MIT. As follows. University of Central Florida's Knight Rider, bot number 13. Bot number 26 from Ithaca, New York, Skynet. Bot number 21 from Oshkosh, Wisconsin. It's called Terramax. Bot number 54 out of Palo Alto, California is called Anyway. From Pittsburgh, PA, Carnegie Mellon University, called Boss. In Corolla, bot 62, Caroline is its name. From Intelligent Vehicle Systems, bot number 15.
Okay, so this video basically show you the urban challenge organized by DARPA in USA, and you will see the effort which is trying to transform a vehicle to become a high-speed mobile robot, all right? And the robot of today could also perform rapid locomotion. And for biped walking, actually, we can identify these four basic actions which could be undertaken by each leg. So we have the action of push, support, swing, and carry. All right. And here is one more example of leg locomotion.
Time for some adventures. Some breathing room. We've stepped out of the tested shop and we are actually in one of my old stomping grounds. I'm standing on one of the training courses for the Alameda County Sheriff's Department in Dublin, Pleasanton, California. Right over there is the bomb range where we blew everything up on Mythbusters. We swam in syrup over there. I learned how to tactically drive backwards in high heels right over there. It's the perfect location to test all of the things about Spot that we want to learn about. His gait, his ability to handle different kinds of terrain. All right, Spot, you ready? Let's go. These rocks and this tunnel underneath the rocks is the perfect first test for him. I'm going to try him over and then I'm going to try him through. All right, Spot. Oh my God. Oh, Spot, you almost did it. I'm going to try this again. This is a really difficult thing for anything to walk over, but we're going to give it our best shot. I think this is largely operator error, but we're just going to keep on keeping on. Here we go. I've adjusted him to a crawl gait, and hopefully this will give him a more stable. Dude, Spot, you are amazing. Holy cow, buddy. That was amazing.
Right, you see this video is quite impressive, right? Okay, and robot can also fly in air, and this is a simulation done by us. Okay, so we have a solution for vision guided landing, and then I just show you the simulated result. Okay, and this is the latest video from Boston Dynamics. Okay, so you see the physical capability of today's robot. If you do a comparison with human beings' physical capability, you will see the gap is quite close. It's not so wide. Okay, not like in the case of intelligence, because the gap between human intelligence and robot intelligence is quite wide. Okay, but the gap between robot motion and the human motion is quite narrow. All right. Okay, so we move on. So you understand, okay, now what is the purpose of doing action planning? Basically, we have a task as an input, then we want to produce a sequence of action as an output, all right? So then we are going to look closely at the input to action planning module, okay? So input to action planning module will be task description in the form of human language, okay? Then what should be inside the description of a given task? So the answer will be the description of a task must indicate the outcome to be achieved, must indicate space constraint, must indicate time constraint, okay? And this drawing show you a series of a task for a robot to accomplish in order to finish the job, okay? So you will see we have a task 1, task 2, task 3, etc. Then for each task, okay, we have a specific outcome, okay? For example, to pass through the door, to climb up the stair, and to walk through this area, which is full of obstacle, etc. All right, so these are the key information which should be contained by a task description. All right, so now I'm going to show you some example, okay, of task description and the action sequence associated with the task description. For example, we have, let's say, this task in mind, okay? Then we can describe this task as follows, okay? A robot arm picks up a bottle at the incoming conveyor. So this box basically simulates the conveyor, all right? On top, we have a bottle. Inside, they are liquid or soft drink, etc. Okay, then place it inside the empty box, okay, which is placed on the outgoing conveyor. Okay, so just imagine this is a conveyor, okay, which will ship out the box, which is full of the bottle. All right. So then this will be a possible version of a task description, which will be the input to action planning. All right. And here is one more example. And the task description will be as follows. So you see an AGV transport part A into the workspace of this robotic arm. Then a conveyor will transport part B, okay, into the workspace of a robotic arm, okay? Then the robot arm will pick up a part A and place it onto the outgoing conveyor. So this is an AGV carry part A, conveyor which carry part B. This is the outgoing conveyor, okay? And this robot is just doing assembly, it's an insertion, okay? So it assembly part A with part B, and then the sub-assembly will be shipped out by the outgoing conveyor, okay? So this is a possible version of a task description. Then what will be the output from action planning module? And the output from the action planning module will be a sequence of action which could lead to the accomplishment of a given task, all right? And then here I shall show you some example. For example, for this material handling task, what will be the action sequence, okay? So you have seen this video. So basically, this is a pick and place task, okay? So therefore, from the video, we could identify this sequence of action. Action number 1, to bring in empty box to the packaging station, okay? So we must place, first, we must place an empty box here, okay? Before we start to do the pick and place, okay? to transport the filled bottle to the packaging station. So you'll see this is the incoming conveyor, which will bring in all the bottle which has been filled with a soft drink. Okay, for example. Then action 3 to pick up a filled bottle and place it into the box and repeat this action for certain number of times. For example, 8 or 6. Okay. Once the box is full, then we ship out the full box. All right. Then repeat the cycle again. All right. So this is a possible version of action sequence as output. And for this example, then we ask you what will be the action sequence. Okay. So this is an assembly task. And here we just show you possible version of action sequence. So action number 1, to pick up a part A from the AGV, then place part A onto the outgoing conveyor. Okay, so this is action 2. Action 3, to pick up a part B from the incoming conveyor. Okay, is a green box. Okay, then action 4, to insert part B into part A. All right, so this is a possible version of action sequence, okay, for this task. All right, then how's about the action sequence for the achievement of this task? This is a task of sorting. So the task is to place the bar to the table of the same color, because we have a bar of green color, red color, purple color. Okay, so we must place the bar onto the table of the same color. Okay, so you see this robot arm is quite smart. All right, so then what should be the possible sequence of action? So from here you see, so action 1 is to pick up a bar of one color, and action 2 to place it onto the table of the same color. Then repeat, okay, these 2 actions, okay, until all the color, all the bar are placed onto the right table. All right, then since we need to place the bar at the middle of the table. After that, then we just okay, place the bar on each table to be at the center of the table. Okay, to pick up the bar on the table, to place it to the middle of the table, and then repeat these 2 actions. Okay, so actually there are two types of tasks. One is to place the bar onto the table of the same color, and also to place the bar in the middle of the table. All right, so this is a possible version of action sequence. All right, then come to this question, because we know what is the input to action planning, what will be the output from action planning, then how to do action planning, what will be the inner process of action planning. Okay, so actually there are 3 ways to do action planning. First way is to use task model. For some tasks, we may have a specific model. Let me just follow the model, okay? And the second way is to leverage on human assistance to do action planning, because today it is still a challenge for robot to read the action description in human language, okay? And in future, our research is to achieve the third way of doing action planning. So it means we use a sensor to guide the robot to do action planning. Okay, so the third way of doing action planning should be a research topic. Okay? So here I just show you, okay, one example of making use of assembly task model. Okay, so you see, if we want to produce this part, then there is a certain sequence for us to follow. Therefore, then we may have action 1 is to assembly part A, part B, then followed by action 2, which will A in part C, then followed by action A3, which will A in part D. Okay, so then we can come out the detailed description of action. Okay. And this is an example which make use of machining tasks. For example, we have an input material in the left-hand side, then this is the output material. So you will see we have a material remover. You see we remove this corner, then we remove a material inside here in order to make the whole one and the whole two. Okay, so therefore, if we know the machining task model, then we can come out this action sequence. Okay, so we start at the side 2 to drill the hole. So that will be action A1, then followed by action A2. A2 is to aid another hole to do the drilling process. Okay, then action 2 will be followed by action 3. So action 3 is to remove material through the milling process. Okay, so to remove 1/4 of the material from the input material. All right, so therefore you have action 1, action 2, action 3. Okay, so you have a drilling process. Action 3 basically is through the milling process. Okay, so we remove the material layer by layer, then we remove 1/4 of the input material. All right. Okay, then in case if the action description is too complicated in a complex environment, then we can leverage on the help of human operator. And this is a simulated result done by us. Okay, so you will see we can use a human language to instruct the robot to undertake the action. Okay, step by step. Okay. So this is an action description entered by human operator, and this is a response from the robot. Okay. So the robot enters the building and will reach the corridor. Now the robot is inside the corridor. Now the robot is inside the room 101. All right, so this is just a demonstration about the result that we have achieved almost 10 years ago. Okay, so if you look at the date, so it's a year 2011. All right, so it's almost 10 years ago. All right. But in future, what we want to achieve is this scenario. Eventually, we want to let a robot to achieve this level of intelligence. Okay, so let the robot to use its own sensor to guide the action planning. All right. Okay. So that will be the future research. We still need to undertake research work in order to achieve this level of autonomy in action planning in all situations. Not in this case. This is a simple case because on the table it's very simple environment. All right. So to achieve this type of demonstration is quite straightforward. Okay. But this just indicates the direction we need to move into until we can achieve this type of scenario in all kinds of situations. Okay, now I'm going to show you some typical scenario of action planning in manufacturing. Okay, for example, we have this task description as an input, which is about sand casting. Okay. So the task is to make use of a molten metal and the mold of a cavity of a specific shape in order to produce a metal part of the shape of the mold's cavity. All right. Then in order to fulfill this task, what should be the action sequence? Okay. So here is a possible version of an action sequence. Okay. So action number one, melting. To melt the raw material. Action number two, to pull the molten metal inside the cavity of the mold. Okay, then to cool, to lower down the temperature and then let the molten metal to solidify. So when the process of solidification has been complete, then remove the mold. Then clean up the mold and do some inspection about the finished part. All right. And here's another task for robot to undertake in manufacturing. And you will see we have this injection machine. Okay. So the task description will be to make use of a molten polymer and the mold of a cavity of a specific shape in order to produce a plastic part of the shape of the mold's cavity. All right. Then based on this task description, what should be the possible version of action sequence? So you will see action number one to close the mold. Action number two to melt and homogenize the polymer. Action number three to inject the molten polymer into the cavity of the mold. Action number 4, to keep the mold closed during injection. Action number 5, to open the mold after the solidification. Okay, and the last action is to remove the finished part, etc. So this is the one possible version of action sequence, right? Then how about the this task of forging? Okay, so the task description is to make use of an impact or gradual pressure to compress hot metal into desired shape. Okay, so this is a input of a task description. Then what will be the output of an action sequence? Okay, if we use the impact to change the geometry of an input material, then you will see action number 1 is to heat up the workpiece, okay, into a specific temperature, and to place the workpiece onto the lower die, and then let the upper die to exert an impact onto the workpiece. Okay, so then in this way we change the shape of the input workpiece. If we use a gradual pressure to compress the input material so that you will take up the shape of the gravity of the die for the forging process. So you will see we have an action to heat up the workpiece, action to place workpiece onto the low die, and to gradually apply lower down the upper die with a certain force, apply the force on the workpiece. Okay, so these are the possible version of an action sequence. Okay, and one more example. Here we have a task of bending, and the description of this task is to make use of a bunch to exert strain along a straight axis on the surface of a metal sheet, which is placed on the die so as to create a desired bending angle. And you know that the most popular bending are these two. Okay, so we have a V bending process and the H bending process. Okay, so you have a bunch, you have a lower die. Okay, so once you apply force onto the metal sheet, then the metal sheet will take up the angle of the lower die. Okay, and in this case we will bend, okay, the metal sheet so as to form a 90-degree angle. All right, okay, then what will be the possible version of action sequence for V bending? First, we need to place a metal sheet on top of a die, and then we must control the bunch to gradually exert a force and press the metal sheet against the die. Okay, then after that, then we lift up, okay, the bunch. Okay, then for H bending, so it's similar. We must place metal sheet onto a die, and then the metal sheet is held against the die by a pressure pad, because for H bending we have this pressure pad. Okay, so place a pressure pad on top of the metal sheet. Then we control the motion of the bunch, okay, to gradually, okay, change the angle of a metal sheet, okay, against the die. Okay, after that, then we lift up the bunch, lift up the pressure pad. Okay, and here is a task of turning. So this is a material removal process. Okay, the description of the task is to make use of a movable cutting tool which act on the rotating workpiece for the purpose of removing layer of material. Okay, so that the original surface of the workpiece is transformed into a new surface of a desired geometry or dimension. All right, so then what will be a possible version of an action sequence? Then you will see first we must load and fix the workpiece onto a rotating head. That means we must fix, this is the workpiece. Okay, rotating head means basically you have a rotating head somewhere here. Okay, then to rotate the workpiece, okay, make this workpiece rotate, then to advance this cutter, okay, so this is a cutting tool. Then when there's a interaction between the cutting tool and the rotating workpiece, then you will see we will be able to remove one layer of surface from the rotating workpiece, all right? And this is a task of a milling. So you will see we have two types of a milling. One, you will see we place a workpiece on the XY table, and we have this rotating tool, and axis of rotation is parallel to the surface of a workpiece. And in this case, the axis of rotation is perpendicular to the surface of a workpiece, okay? So the task description will be as follows, okay? The task is to make use of a rotating cylindrical tool with multiple edge in order to remove material from a movable workpiece so as to produce a workpiece with the desired surface profile, all right? So this is a description of a task. Then we need to identify what should be a possible version of action sequence, okay? So here I just highlight to you or give you one possible version of action sequence. Action number one is to attach and rotate cylindrical tool, okay? That means you must attach this tool onto the rotating head, okay? So second one is to fix workpiece on the movable table. So you see we have a XYZ movable table or XY movable table, okay? So in this case, I guess it's XYZ. So this table can provide motion in X direction, Y direction, and the Z direction. And in this case, it's the same. So we have an XYZ table. So actually, XYZ table could be treated as a XYZ robot or Cartesian robot. Okay, it's a robot with a 3 degrees of freedom, which could output 3 translational motion. Okay, so you can actually treat this one as a XYZ robot. This is another XYZ robot. Okay, all right. So basically means what an XYZ robot hold this workpiece. Okay, then to fit the workpiece, that means by controlling the XYZ table or XYZ robot, then we can control the location of an interaction between the surface of a workpiece and the rotating tool. So in this case, the rotating tool is at the fixed location, all right? So by changing the interaction location, then we will change the profile of the workpiece, all right? So this is this scenario. Then how's about this assembly task? Okay, welding is an assembly task. Welding means to join 2 workpieces together by adding additional material. Okay, so after solidification, then these 2 workpieces will join permanently together. Okay, so this is a task description. Then you will see, in order to operate this process, we must have the welding gun. Okay, so welding gun will supply filler metal and also supply thermal energy to melt the filler metal, okay, in order to deposit additional material, okay, between the interface, okay, of the 2 workpieces to be joined together, okay. So then this is a possible version of action sequence. First, to place the 2 workpieces together so that they form a desired joint, such as you see joint like this. So this is a parallel coplanar. Okay, this is a perpendicular, and this is a parallel but with offset in the vertical direction. And this is a perpendicular. All right. Then once we form these kinds of a joint, then we must supply additional material, okay, inside in order to join these 2 workpieces together, okay, to place 2 workpieces so as they form a desired joint, to generate and apply heat, and also maybe we may want to apply the pressure along the contacting surface. At the same time, we must supply the filler metal, okay, if needed, okay. So after that, then we need to do the inspection about the quality of the well. Okay, all right. And then this is another process of assembly. Okay, then the task description is to make use of a fastener, which is to mechanically attach two or more parts together in order to create a final product of a desired structure or mechanism. Okay, so you will see. Okay, we can dismantle. Okay, the assembly. And then for you to see actually this output, this finished product consists of these individual work piece. Okay, and then we can, based on the task description, we can identify this possible version of action sequence. And this video show you one more example of the assembly process, which make use of a temporary fastener. Okay, so we can dismantle all the part or put all the part together. All right. Okay. So you see, action number one is to place two parts together with the correct alignment to insert fastener and to tighten fastener. All right. Okay. Then by repeating this action sequence, then we can add more part together in order to form this complicated product. Okay. So you see, now this is a sequence of action for us to do the assembly. So all right. Okay. Then what will be the future goal? Okay. In robotics research with regard to action planning, because we understand if we leverage on human intervention to help a robot to do action planning, then there's no issue because we can leverage on human intelligence. But our future goal is to let robot to understand task description, and based on the understanding of the task description, then eventually robot should be able to decompose a task into a sequence of action. So this is a future goal of doing task, doing action planning. All right. Okay, so that's all for the study of lecture 2 of module 1. The key takeaway from lecture 2 is for you to understand that the input to action planning is a task description, and the output from action planning is an action description. Both task description and the action description are based on the use of a human language. Therefore, it is difficult for today's robot to master or to understand the meaning of task description and also to formulate the meaning of action planning. So this is why today we still need to leverage on human assistance to help a robot to undertake action planning. But the future research is to achieve autonomy by robot at this level. Okay, so that will be a good research topic for you to follow. For those of you, if you want to continue the study all the way to achieve the obtention of your PhD degree. Okay, so this could be an area of research for you to pursue. All right, so we end this lecture 2, and I'm looking forward to seeing you in lecture 3.